So I wanted to talk about the kinematics of spin. Basically, what was discovered is that spin can be treated like a function of vectors, basically. So in what we've done, everything we've done so far, in all the cases that we've studied, we always consider the wave function psi to be a scalar. So it always works out to be something like a Legendre polynomial, a Laguerre polynomial, but it's always just some function. So with spin now, what we're really doing is taking one function, say when the particle is in a spin up configuration, or if it has a spin eigenvalue of h bar over 2, and then we're transforming it into a wave function that now has a spin down configuration, or which will give you an eigenvalue of minus h bar over 2. So what we're going to eventually develop is a vector function for the wave function. So psi, you could put an arrow on top of it if you wanted to. And so that's the idea, is that we're going to now create this function which has components, but the components are not numbers. The components are actually going to be other functions. So you can imagine if I had an n component wave function, so psi, capital Psi, I'll put the headers and the footers on it, and I could write it as a row vector of psi1, psi2, psi n. So now we're going to figure out, not only do we have to figure out what the wave function is, we have to figure out what each wave function component is going to be. And so since the spin acts like an angular momentum, it has units of angular momentum, and we can combine it together with what we know already for the orbital angular momentum. So if we're going to do a transformation of a system that has both a orbital rotation and a spin rotation, why don't we just add them together? So I'm going to write down a transformation of a state psi prime is equal to the identity minus I epsilon over h bar, the orbital angular momentum operator, plus the spin operator, and all of that is acting on my function psi. I'll make these brackets right here. So this is the same thing we did when we wanted to make a transformation around the z-axis for the orbital angular momentum. It's just that what we did is we made a Taylor series of the operator and truncated after the first term, and we're taking an infinitesimal rotation around epsilon. So we get an infinitesimal angle, basically, of epsilon. Okay, but like I said, these states are vectors, and so what I really could write down is this vector psi1 prime, psi2 prime, psi n prime is equal to the identity matrix 1, 0, 1, 0, dash, 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 1, and then this would be 0, 0, like this. So that's the identity matrix, minus I epsilon over h bar, and I have a rotation, the orbital rotation, minus I h bar the derivative of phi all along the diagonal, and then these are zeros every place else. So that's the LZ minus I over H bar SZ, and then all of that is operating on the state psi 1, psi 2, dot, 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 all the way down to psi n. So now we can write the wave function. If we write it as a row or a column vector, then our operators now become these matrices. So we can clean it up a little better by saying we have a total angular momentum in the operator operating in the z direction, J, which is LZ plus SZ. So we're going to combine the two together. So now I can write my state in a little more compact form of I minus I epsilon over H bar JZ operating on the original wave function state psi. And that would mean, so that's just in the rotations about the z direction. The total angular momentum would be J with a vector arrow on it. The total angular momentum vector plus the spin vector right here. And since J is a total angular momentum, it should operate like an angular momentum. And so we should get these commutators where J, I component commuted with J component, and that gives me I, H bar, the sum, K, the Levashevita tensor, J, K. Anyway, I mean, so just as a few examples, what you should get is Jx, Jy is equal to I, H bar, Jz. Or you can cycle through them. So these I, J's, and K's are, you can think of them as in Cartesian X, Y, and Z, or if you think in terms of spherical components, it's R, theta, phi. We'll stick with the Cartesian. And so if we cycle through them, we would get all the commutation relations that you would get for angular momentum. And we kind of worked this out in the chapter on angular momentum. But there we just worked out the case for the orbital angular momentum, L. So if you remember, it had the same mathematics. So Li, Lj is equal to I, H bar, the sum, over K of Levashevita, I, J, K, and then Lk. Yeah, and so we can get the commutators Lx, Ly is equal to I, H bar, Lz, or Ly, Lz, commutator is equal to I, H bar, Lx. If we cycle through the different components of X, Y, and Z. So that, if we follow this by analogy, should tell us something about the spin mathematics, because J is just the addition of orbital angular momentum and spin. So therefore, we can show that Si and Sj, the commutator of those operators, should give me I, H bar, the sum, summing over K, which would be X, Y, and Z, the Levashevita I, J, K, that tensor, times S sub K. where you're really summing over all of the indices that you would get. So just as an example, if I want Sx, Sy, that's going to be equal to I h bar times, now we would have x, y, x, s, x. So k, the first k is x, plus x, y, y, s, y, plus x, y, z, s, z. So that's that sum over the index k. So really I should have written k goes from 1 to 3, like this. But remember, for the Levi-Civita, that if I repeat any of these indices, it's 0 if I is equal to j, or j is equal to k, or I is equal to k. Any repeated index, like the x, y, x is going to be 0. Epsilon x, y, y is 0, and x, y, z is equal to 1. So in the end, the commutation relation x, sx, sy is going to be equal to I h bar s z. So this should be true. So just like for the L's, the orbital angular momentum, or the J's, the total angular momentum, spin should also follow these rules. But the caveat is that this S operator is not necessarily just a number. It's a matrix, because we want to transform a vector, so say like a column vector, like we did before, into another column vector. So these S operators should be matrices. So if we now just consider the case of a fermion, a fundamental fermion, so like an electron or a quark, then there are two possibilities for the spin. You're going to have spin up, basically positive h bar over 2 eigenvalue, or spin down, negative h bar over 2 eigenvalue. So we've got these two eigenvalues. So if now that means there are two components. There's a spin up component, a spin down component. So that means that our S operators need to be 2 by 2 matrices to transform the particle from its spin up configuration to its spin down configuration. And these 2 by 2 matrices have to match with the commutation relation, which I'll write again as Si Sj is equal to I h bar, the sum of k goes from 1 to 3 of the Levi-Civita times Sk. So we have to find 3 2 by 2 matrices which fit with this commutation relation. And so to round out this video, I will leave you with the answer. There actually are a couple answers you can have, but the simplest one, the one that most people use, are Sx is equal to h bar over 2, 0, 1, 1, 0. Sy is h bar over 2, 0 minus I, 0. And Sz, which is h bar over 2, 1, 0, 0, minus 1. So this is one possibility for the spin operators. It's actually probably one of the easiest ones. So what I'll show, so I'll stop here and I'll show in the next video that these operators that we've chosen, the solution we have, will fit with the commutation relationships.